uma grande satisfação poder estar aqui novamente após mais de 2 anos. Então, eu acredito que todos perceberam, sentiram a dificuldade que nós enfrentamos ao longo desses mais de 2 anos. Nós organizamos uma série de webinários, né, seminários que foram, digamos assim, divulgados e apresentados para vocês usando plataformas digitais, e eles vão continuar existindo, né, mas toda vez que a gente pode voltar a se encontrar no auditório, né, estar próximo das pessoas que estão apresentando, perceber se o que as pessoas estão olhando, o que elas estão vendo, eu acho que isso tem um significado muito diferente. Então, é muito gratificante para a gente, né, poder perceber um auditório praticamente lotado. A gente sabe que agora é um horário de aula, né, muitos professores, muitos alunos estão envolvidos com as suas atividades acadêmicas, mas mesmo assim a gente tem praticamente a lotação máxima aqui, e isso é bastante interessante. A palestra de hoje ela é uma palestra bastante especial. Tá? Nós temos um acordo de cooperação com a Universidade de Melbourne desde 2016, né? E ele foi recentemente, se eu posso usar a palavra, renovado. A gente não renova o acordo de cooperação, a gente faz um novo, mas a gente renovou esse ano. Né? Então, no primeiro contato, o professor Ashokkumar veio até Santa Maria, né, com o interesse de fazer um acordo de cooperação conosco. Esse acordo foi firmado e nós, esse ano, tivemos a oportunidade, né, de retribuir a gentileza. Então, o professor Érico e eu podemos ir até a Universidade de Melbourne para a gente novamente firmar esse novo acordo de cooperação. Esse acordo ele é bastante, digamos assim, oportuno, porque a Universidade de Melbourne ela figura entre aproximadamente as 30 melhores do mundo. Isso pode não parecer assim algo tão significativo. A UFSM está entre as 20 melhores do Brasil, para a gente ter uma ideia, e nos rankings mundiais ela figura entre as 1000 melhores. Então, quando a gente fala de uma universidade abaixo das 50 melhores, a gente está falando de uma universidade altíssima. E a pesquisa que o professor Ashokkumar faz reflete, né, o nível da formação, o nível da instituição. Isso, quando ele vem aqui e profere uma palestra para a gente, profere um curso, como alguns alunos estão tendo a oportunidade de fazer, ou até mesmo uma disciplina de curta duração, como é o caso que está acontecendo agora, a gente traz esse alto nível, né, esse nível de exigência para dentro da nossa instituição. Isso só faz com que a gente cresça, isso aumenta a qualidade, né, dos nossos alunos que estão sendo formados, isso aumenta a qualidade do nosso corpo docente. Temos professores que estão participando das palestras, né, dos cursos que o professor Ashokkumar está ministrando ao longo da semana, isso está sendo muito gratificante para todo mundo. Então, temos alunos de diversos grupos de pesquisa, de diferentes áreas, né? Além da química, temos pessoas, né, da engenharia química e dos alimentos também aqui da UFSM, assim como pessoas que vieram de fora, né, da Universidade Federal de Pelotas, que estão podendo prestigiar. Tudo isso só aconteceu graças a esse programa de internacionalização, né? É um edital que foi lançado pela FAPERGS, né, e que nós tivemos uma proposta que ela foi redigida, submetida pelo professor Érico e ela foi aprovada. Fruto disso, nós temos essa visita, né, que desde o início da semana está, digamos assim, ofertando cursos com o melhor que ele tem, que é o conhecimento dele, está compartilhando conosco. Tá? Ainda fruto desse programa de internacionalização, dentro de alguns dias, a gente vai ter uma outra visita de um outro professor internacionalmente conhecido também. E o programa de pós-graduação em Química, ele vai, mais de uma vez, ofertar uma disciplina de curta duração. Tá? Todos vocês serão avisados, a gente fará uma divulgação dentro das nossas limitações de espaço, né? E mais uma vez a gente espera poder contar com a presença do maior número de alunos possível, porque isso só fortalece a formação e, digamos assim, a atuação profissional que vocês vão poder exercer, né, após finalização dos cursos de pós-graduação. Tá? Então, sem mais delongas, esse seminário está sendo organizado pelo programa de pós-graduação em Química e nós temos a honra de contar com uma mediação feita pelo professor Érico Flores, o qual vai fazer a apresentação do professor Ashokkumar para vocês. Então, professor Érico, muito obrigado. né, por ter feito o convite para o professor Ashokkumar e disponibilizado um pouco do tempo dele para o nosso programa, e a palavra é do senhor.
Obrigado, César. Obrigado pela apresentação e comentários. Você colocou o currículo dele, aí fica mais fácil de falar. Mas o professor César tem resolvido muito bem a importância da vida do professor Ashokkumar aqui para Santa Maria. É a segunda vez que ele está vindo para cá, outra vez em 2016. Foi o primeiro contato com eles de longas tratativas para conseguir que ele viesse. Quando eu ler o currículo dele, você vai entender melhor a dificuldade de trazer uma pessoa de tal trabalho com uma importância fácil. Eles têm uma série de atividades, uma série de compromissos, responsabilidades na universidade dele também. E a nossa primeira ideia antes de vir para cá, a gente conseguiu, foi que ele estava indo para um congresso em Roma, depois foi para o mundo, e aí conseguimos que ele viesse para cá. Foi difícil lá, gente, foi muito difícil conseguir, mas ele conseguiu gentilmente o espaço na agenda dele de maneira a conseguir estar com a gente. Ele gosta muito de Santa Maria, né? Essa é a primeira vez que ele veio. E uma pessoa que criou muitos grupos ao redor do mundo, tem contato depois com os grupos no Brasil, o que nos deixa muito honrados de fazer parte dessa rede de interação que ele tem. Ele não é da nossa área específica, do nosso grupo de pesquisa, trabalho da área de química, que trabalha também em outras áreas de farmácia, nós trabalhamos na parte de legislatória a lei que legislatória dele. O professor César mencionou que a Universidade de Melbourne, isso é uma coisa que se destacada, está entre as 30 melhores universidades. Você tem uma ideia, a USP é a melhor universidade da América Latina, ela está na posição 250, não é de 200 a 250, mas é posições. A dele está em posição 30. Cada uma posição acima de 250, nós temos 300 universidades competindo com você em alto nível. Então, a universidade deles realmente é forte, séria e com muito impacto internacional. Uma das coisas que é importante mencionar, que é importante para o nosso programa de pós-graduação em Química, que até agora, o início deste ano, eu e a professora Paula Mello, representantes, estivemos à frente da Secretaria de Apoio Internacional da UFSM. Entre as atividades que a gente fez, que nos orgulham muito, as operações com países da América Latina, que a gente iniciou várias operações pioneiras, nós temos muito orgulho de dizer que conseguimos, pela primeira vez na nossa gestão, conseguimos os primeiros acordos de cooperação internacional com países da Ásia, como China, e agora, mais recentemente, a Índia. Isso nos deixa muito orgulhosos, porque abre um espaço de cooperação oficial da nossa universidade, que permite mobilidade de docentes, professores, servidores de modo geral, mas também projetos de cooperação de pesquisa. Isso é muito importante, porque hoje em dia as universidades, os programas de pós-graduação, são cada vez mais e mais ranqueados em termos de redes de colaboração internacionais. Ninguém mais está preocupado com redes de cooperação nacionais, que obviamente são importantes, mas muito mais com redes de cooperação internacional, com pesquisadores de ponto superior. Eu vou ler um breve resumo do livro dele. Talvez eu atrapalhe alguma coisa que eu vou traduzir em português antes de eu ler. O professor Muthupandian Ashokkumar, talvez nós chamemos ele informalmente de Ashok, como ele se apresenta. Ele é da área de fisicoquímica, que se especializou em sonoquímica. Ele é professor na graduação e pós-graduação na área de química, escola de química da Universidade de Melbourne, e também é um membro do corpo acadêmico do Ultrasonics. Ele, correntemente, atualmente, ele é o professor adjunto, ou assessor adjunto nas relações internacionais da Universidade de Melbourne. Essa é uma das razões que ele veio para Santa Maria. Ele tem uma atuação institucional da parte internacional forte da Universidade de Melbourne. Ele é assessor da conta deles. Ele é um renomado, mundialmente conhecido, com cerca de 25 anos de experiência nesse campo, tem desenvolvido um grande número de técnicas novas, caracterizando, por exemplo, bolhas de aplicação acústica, e tem tido muitas grandes contribuições na sonoquímica aplicada para materiais, a parte de alimentos, processamento, pesquisa O grupo de pesquisa dele desenvolveu novos sistemas de processamento de ultrassom. E a pesquisa mais recente dele também envolve a síntese assistida por ultrassom de grupos funcionais para nano e biomateriais, que podem ser usados para a produção de energia, muito importante, um dos grandes focos hoje do mundo, para a regeneração ambiental e também muito importante para diagnóstico e terapia medicinal. Tem recebido nos últimos anos mais de 15 milhões de dólares de projetos na indústria, e aqui acho que um dos pontos principais de destaque dele, ele é atualmente o editor-chefe do periódico Ultrasonics and Sonochemistry da UFSM, cujo valor de impacto é um dos mais altos da área de química, 9,43. Ele também editou e editou vários livros, capítulos de livros, publicou quase cerca de 500 artigos, né? Todos eles deu uma olhadinha, esse de altíssimo poder de impacto. E tem um ministrado 77, um dos mais altos da área de química. Tem publicado em periódicos de altíssimo impacto e já apresentou mais de 200 palestras plenárias internacionais e também em conferências da região dele e também internacionais. Ele, com toda essa experiência, para nós, uma lei longa, por enquanto, eu mergulhei em Santa Maria, e não científicos do bioquímica, do your appointments, the six responsibilities that you have in our university, but they are glad and they thankful to have you here. As Professor Ashok, with his experience of past, I simply knows this. In some conferences, he is called as Mr. Ultrasound. With the knowledge of ultrasound. Is that a pleasure, please? Right.
Good morning, everyone, and thank you, Professor Ross, for the kind introduction, and also for the invitation for me to come and share my research topic or experience with your students and staff here. And I'm really glad that I'm spending almost a week here. And those who are attending the course for the past 2 years, 2 days, you will see that some of the slides that I'm sharing are similar. The presentation today will be a condensed version of the course that I'm delivering. So please apologize if you feel that I'm kind of repeating what you already know. And again, thank you all for coming to this lecture today. And the hope is that I will give you an overview of what we do in the ultrasonics and sonochemistry area, and how that is linked to what we call the lead technology. And then we'll have a time for asking me questions if the things are not clear. And you don't have to wait until the end of the lecture. So during my lecture, if you have some questions, please feel free to interfere and ask questions. Thank you. And as you can see from the topic, basically I'm trying to demonstrate that ultrasonic and sonochemistry can be considered as a technology for free chemistry of getting materials using green processing. And as Professor Floss told you, I have multiple roles at the University of Melbourne. Two primary roles are that I'm a professor in chemistry, so I teach physical chemistry primarily for undergraduate postgraduate students. And also I have the assistant deputy in charge of international reform, which looks after the international relationship between Melbourne University and the international institutions, including the University of Santa Maria. I think we've had the MOU between us, our research collaboration, student engineering, and so on. And one of the students from Professor Flo's group is coming to Melbourne in October for 6 months, and I'm hoping that many of you have the opportunity to come and experience. Thank you. So I'm just going to briefly introduce the Melbourne University to you. for a couple of minutes before we move on to the lecture material. And I said I will have this international relations portfolio that I look after at the University of Melbourne. Melbourne University was established in 1853, the second oldest university, and it was pretty much established during the British time. So the English people started settling in Melbourne, Australia. They started the second oldest university in Melbourne. But currently we have a mixture of traditional buildings and also modern buildings for teaching purposes. We have 7 campuses. Our campus is the main campus, which is part of the city. So you can see the city center here. And our campus is located north of the city. And walk to the city center within 10 minutes time. These are the residential colleges where students stay, interstate or international students. And this is the main entrance to the Parkville campus. The rest of the campuses are more purpose-built. For example, the South Bank is for fine arts, and the Berkeley campus is for veterinary science and so on. And the University of Melbourne is ranked #1 in Australia with the Times Higher Education ranking process. And globally, we are in top 35 in the past 10 years or so. And normally, we have about 70,000 students studying both undergraduate and postgraduate courses. It is not a university, what it means is they teach everything: arts, engineering, science, law, medicine, you can think of. So we have about 40% of that 70,000 students international, primarily from Asian countries. So the top most one is the China. Maybe around 60 to 70% of the international students from China. The rest of the students come from other countries, including India, Malaysia, Singapore, and so on. Just an introduction to my team. I have a strong international collaboration. So everything that I have learned over the past 25 years, that has been contributed through the research collaboration with a number of international institutions. So you can see that I have a substantial number of international collaborations. And not still added the University of Santa Maria here, this is the whole slide. And I have a number of postdocs who contributed to the learning that we have that I was going to great scientific and master's and PhD students. So currently I have in my group about 6% PhD students. I will limit the place you can only have a maximum of 6 students, PhD students. Very push it to 7 or 8%. So that's kind of, again, I would like to acknowledge all the contributions from the postdocs and collaborators and PhD students. Some of the information that I've shared today are the things that I learned from through the collaboration and contribution from my students and postdocs. Okay, the first thing that we need to know, is how ultrasound can be used to induce processing or chemical reactions. Okay. Those who attended the course for the past 2 days, you know in detail what acoustic gravitation process means. This is a simple picture of what acoustic gravitation is and how it is kind of leading to generation of large amount of energy that can be considered as clean energy by doing some clean processing. So if I take any liquid, whether it's water or organic liquid, I will have some dissolved gas bubbles in that liquid. So when you pass ultrasound waves are basically compression and rarefaction pressure cycles. So whenever I speak, I have sort of transducer in my throat that vibrates. And then the sound waves go through the medium, air medium, and you have another transducer in the ear that receives the sound waves and then registers in the brain what I'm talking. The same thing here, we have an acoustic pressure wave passing through the liquid. So when the liquid around the bubble, when that experiences the compression or rarefaction cycle, then the bubble starts to respond to that change in the pressure around the bubble. So in this case, if I look at the rarefaction cycle, the bubble, the liquid around the bubble is experiencing this low pressure. So that leads to the expansion of the bubble. And then when the compression cycle comes, then the bubble starts to shrink because the pressure around the bubble is higher. And that cycle starts to repeat. So simply what the bubble is trying to respond to the change in the pressure rate around the bubble. And what you can see here is that bubble not only oscillates for this pressure change, it also grows in size. That growth is by means of a process called rectified diffusion process. You will not have time to go and understand what that rectified diffusion process is because that itself will take 20 minutes. The idea for this kind of overview lecture is not to go into the details of any process, but to give you an overview of how things work. So that later on, if you want to focus on a particular aspect that you want to have clarity, please feel free to contact me and send me more papers, and then you can read them to understand more. Anyway, so the bubble starts to oscillate and grow and reaches a size called resonance size. At that point, the bubble grows to the maximum and collapses. And that's what you see in this video today. So you can see that it's a special technique that we use to monitor the growth and collapse of the bubble. And you can see it is growing, and then collapsing, the same bubble grows again, collapses again, and so on. So the time scale, for example, if I'm operating the ultrasonic at 20 kilohertz, time scale is about 50 microseconds. So this whole process happens within 50 microseconds, in growth and collapse. And the other aspect that you can see here is the growth process is relatively slow. Collapse is very fast. That is the important part. Fast collapse leads to some sort of near adiabatic process. So those who are assuming that most of you have some undergraduate chemistry knowledge. So if you look at your thermodynamics, whenever you have a volume change, when volume is collapsing, there's a change in volume. That volume change corresponds to work done. W is equal to P delta V. In this case, the bubble is not doing any work. So the work is going to be converted into heat. So the bubble is collapsing by near adiabatic process to generate large amount of temperatures. And it can measure experimentally and calculated theoretically that the temperature can be 2000 Kelvin, 5000 Kelvin, 50,000 Kelvin, sometimes even 100,000 Kelvin, based on the experimental conditions. Okay, so you just need to believe at this stage that the bubble collapses near adiabatic, you generate a large amount of temperature and pressure within these bubbles. So what happens is during this expansion process, whenever the bubble expands, you first create a vacuum. So when you create a vacuum, molecules around the bubble, like solvent or solutes, like gas molecules that are dissolved, they diffuse into the bubble. So when the bubble is now having some gas molecules or solvent vapor molecules, and if these molecules are subject to high temperatures, that's where the chemistry starts to happen. So we know that if I take a solvent as water, we'll have H2O, hydrogen, oxygen, hydrogen. So you have a hydrogen, oxygen, hydrogen bond. And if I provide heat, I can break that bond. So it's an endothermic breakage of the bond that leads to the generation of hydrogen atom and hydroxyl atoms. So like this, you can generate what we call the primary radicals. Once you generate radicals are very, very reactive. We are going to have some examples later on. All you can use these radicals for making some nanomaterials. Okay. And we call this green process because we're generating these radicals not from chemical additives, we're simply creating these radicals from water. And when these radicals react, they go back to water or hydrogen. So you're not also creating a new pollutant. That's what we call this as a clean process. Something that also happens is the light emission. Because of the high temperature, some of these molecules are excited to excited state, then they return to ground state emitting light. That light is called sonoluminescence. But that's not the main focus of these lectures. I'm not going to talk about the sonoluminescence because of the time limitation. What happens is that there are other physical forces that are generated. For example, when the bubble is collapsing, there's a small microjet that is produced due to asymmetric collapse of the bubble on the surface of the container. And these microjets have very, very high kinetic energy. What it means is this kinetic energy can be used to make small pits, holes on the surface of particles that increases the surface area of this particle. So if I use this particle for catalytic reactions, then I can increase the surface area, find the surface area, or I will be the reaction efficiency. So some of these physical effects, we can use it for various chemical reactions. In addition to that, when the bubble is collapsing, the pressure is also very high. Decrease the volume, the pressure becomes much higher. And that pressure is released back into the system when it's sort of shock wave. That shock wave has high energy also. Okay. So what that can do is increase the mass transfer. You know, in chemistry, mass transfer is critical. You want to increase the collision between molecules or collision between particles in order to improve the process efficiency. So the physical forces that we generate can be used for increasing the mass transfer and hence improving the reaction efficiency or process efficiency. Here I'm just going to show you a small video clip to show how strong these forces are, physical forces are. And please click on it. So you can see that I have this small ball trapped in a capillary wall that is oscillating, that have a transducer here. And that oscillation generates really strong forces, physical forces, that moves the particles in that capillary. So if you imagine that instead of having these particles, we have molecules, they'll be moving around very fast. Increasing the collision between molecules, then I can increase the rate of chemical reactions. Particle-particle collision may lead to some processing applications. So this kind of physical forces can be used for many applications that we will look at later on. Here we are just showing that the same shear forces can be used for making an emulsion. So I have some water, I have some oil, the ultrasonic oil is coming from the top. So you will see that as soon as it starts sonicating, I will form a nice water and oil and water emulsion. So these kind of physical forces are really good and strong for making processing applications of applications. The chemistry I think I already mentioned to you earlier that when I have water molecules within the bubble, I have large amount of heat produced. That heat can be used to break the water molecules into hydrogen atom and hydroxyl radicals. Hydrogen atom is a reducing agent. Hydroxyl radical is an oxidizing agent. So I can do redox reactions, oxidation reaction, and reduction reaction. And chemistry is all about oxidation reduction. Nothing special. Okay. So simply I can use these tabulation bubbles to generate redox radicals. Then I can do oxidation reduction reaction. Again, if I want to do this reaction conventionally, if I want to do a reduction reaction, I have to add a reducing agent. If I want to do an oxidation reaction, I have to add an oxidizing agent. But here I'm not adding anything extra from external. I'm simply soluble water and generating the redox bubble. That's why we call this green. No external chemicals being added to the chemical reactions. Okay, so that's kind of very brief account of the acoustic tabulation process. So what our group has been doing for the past 25 years or so, ever since I started my job at Melbourne University in early 96, I've been working in the field of sonochemistry. And maybe just 10 years or so, we focused on understanding the basics or fundamentals of acoustic gravitation. So if I want to summarize everything, it will take much longer time. But the key thing is that unless we have good control over the acoustic gravitation process, I will not be able to control the chemical reactions that I want to, or processing applications that I want to do. So after that, basically, we moved into some applications. So our kind of group has been focusing on applications of acoustic gravitation in energy, environment, health, and food applications. I think today we will be focusing on a little bit on the material synthesis, a little bit on food processing, a little bit on bioprocessing. So that's where we will be focusing on. The first application that I want to show you is how to use the chemistry part of the acoustic gravitation process for making nanomaterials. I'm just going to take a simple example of using these radicals that we generate to reduce metal ions to form metal particles. And those metal particles can be then used for other applications. You know, nanometal particles are used in catalytic applications. Nanometal particles are used in biomedical applications and so on. So we're not going to go too much into the details of those. I'm just going to demonstrate here that you can use the sonochemical process to make some nanomaterials for application purposes. For that, I'm using gold as an example. This AU here is gold chloride solution. So in this case, the gold has 3 positive charges. And as I mentioned before, we are generating hydrogen atom. Hydrogen atom is a reducing agent. So if I have 3 of those hydrogen atoms generated by this gravitation process that we put here, and then react that with the gold ion, I can generate gold atom. Then gold atoms can join together to form gold nanoparticles. But this, I said, this is a simple example, but you can use any metal ion, silver ion, platinum ion, ruthenium ion, anything that you want to make this a nanoparticle. And how do we know that this reaction is happening? I can simply use nearly visible absorption spectroscopy to monitor the formation of gold particles. For example, if I take the solution just before solidation, gold chloride solution, there is no any absorption in the visible region. At 0 minutes means at this part of the reaction. Now as it starts sonicating, there is an absorption that is growing from 530 nanometers. That absorption value is due to plasma absorption of the gold particles. So if I talk of silver, silver has an absorption value around 400 nanometers, or 380 nanometers, and so on. So for each metal, they will have specific absorption that I can use to follow. So in this case, it's a very simplified mechanism. But again, I keep telling that here we are not adding any external things to make these external chemicals to make the gold particles. That's why we call that as a clean process. Okay, trying to play with the chemistry. So if I know some chemistry, then if I go back to our original this particular case, where we know that we are generating hydrogen atom, which is a reducing agent, hydroxide atom, which is an oxidizing agent. But if I want to do only reduction reaction, this is what we are trying to do for gold formation or any metal formation, then we are wasting the hydroxide atoms. It's half of the radicals that we are generating are not being used. But if I know a little bit of chemistry, then I can convert this oxidizing radical into a reducing radical. That's what we are trying to do here. By adding a small amount of alcohol, like ethanol or propanol, I can convert both hydrogen atom and hydroxide radical into alcohol radical. An alcohol radical is a reducing radical or a reducing agent. So simply I'm converting non-spacing agent into a reducing agent, which means I can double the formation of gold formation, gold particles. In addition to that, what you can also see here is that in the absence of the alcohol, the absorption band is much broader. In the presence of alcohol, the absorption band is much narrower. So what it does, what alcohols do is, alcohols not only act as a reducing agent here, also they're acting as protecting agent or capping agents. So you form a nanoparticle fusion can lead to the large number of particles, large size particles. But if it has some alcohol absorbed to the surface, then fusion between gold particles can be prevented. That means you get smaller size distribution. That smaller size distribution is the one that is responsible for this narrow absorption band. So that's the electron microscopy of these gold particles. You can see that we get different shaped particles. Some are spherical, some are triangular, and some are kind of rod-like structures. Later on, I think I may have a slide to show that we can control the shape of the particles also. So here, again, it's very hard for me to explain the whole thing because of the time limitation. But basically what we're trying to do is we're trying to control the size of the gold particles that we produce by controlling the frequency of ultrasound. So what we know is when you use low frequency, like 20 kilohertz, then the amount of radicals that you generate, or the number of cavitation bubbles that you generate, is very low. When you have a low number of cavitation bubbles, you generate a low number of radicals. At that point, whenever you try to form or control the particles of any metal or any inorganic particles, there are two processes involved. One is the nucleation, the other process is growth. Okay. If I can have the nucleation rate greater or higher than the growth rate, then I get small particles. How do we control or how do we make the nucleation rate higher? I can produce more radicals. If I produce more radicals, I can produce more gold ions. That means the nucleation rate is much, much higher. So here you can see that at 20 kilohertz, we are producing less number of radicals, so the hydrogen peroxide concentration reflects the number of radicals that we generate. So the methodology that we follow, analytical methodology. So you can see that at 20 kilohertz, we don't generate much radicals. When we go to very high frequencies like 300 kilohertz, we generate more radicals. And then when we go to very, very high frequencies, the amount of radicals that we generate decreases. Okay. So again, I may not be able to fully explain to you how this trend is happening, but simply what you can see is that I can control the amount of radicals produced by controlling the frequency. And that means I can control the nucleation rate. That's what this shows. Here is the rate of reduction of gold ions, or the rate of formation of gold nanoparticles. You can see that the rate of gold formation is very low, and the radicals are low. The rate is higher, and the radicals are high, and then it decreases in high frequencies. So my expectation will be that if I follow the particle size will be relatively large at 20 kilohertz because the nucleation rate is lower. Particle size will be small. When I operate the ultrasound at 200 to 400 kilohertz, because that's where I produce more radicals, the nucleation rate will be much higher, and then it will decrease. And that's what we observe. So you can see that I get much bigger particles, and the radical generation is very low, or the nucleation rate is low. And then I get much smaller particles when the radical generation is high, where the rate of nucleation is much higher, and then it decreases again. Okay. So those who attended my course, we know why this is happening in terms of why the radical production increases and then decreases. We do have a paper that is published on this aspect. So for those who really want to understand, please feel free to contact me and I will explain to you. Simply what we have demonstrated here is that I can control the size of the particles, controlling the frequency, which in fact controls the rate of nucleation. And that's what we see here. There's a linear function between the size and the rate of nucleation, irrespective of the frequency that we use. Whether we use ultrasound or conventional chemical methodology, this is valid. So if you want to make small particles, you simply need to increase the concentration of the reducing agent so that you can increase the nucleation rate. So that's the knowledge that you need to have. I think we also spoke about this with our students who are attending the course, that if I want to make single metal nanoparticle, like silver particle or gold particles or platinum particles, there are conventional chemical methodologies where, for example, I can add some sodium borohydride or ascorbic acid or any reducing agent, and I can make large quantities of these nanoparticles very quickly. So this chemistry may not be an advantage, except that if you want to be purely clean, no external reagents added, then you can go for sonochemistry. But if you are going to go for an industrial process where you want to make hundreds of kilograms of these nanoparticles, that's sonochemistry may not be a viable process. They can simply go for any conventional methodology. But here I'm just showing one example where the use of ultrasound is the only option where if you try to use conventional chemical methodology, it may not be useful. So that I'm just demonstrating this example where methanol fuel cell, if you take a methanol fuel cell, you have electrodes which are made of carbon, both anode and cathode. Both electrodes are deposited with platinum particles, nanoparticles. Platinum nanoparticles function is to improve the redox efficiency, electron transfer efficiency. If you look at the mechanism of the methanol oxidation process, you can see that methanol absorbs the platinum particles and undergoes some redox reaction. During that process, we generate carbon monoxide. Carbon monoxide has very strong affinity to platinum, so it's very difficult to remove the carbon monoxide. That leads to what we call the poisoning of the electron. So the intermediate does not want to leave. That means it blocks the catalytic surface. So those who are working in electrochemistry then suggested that if you have ruthenium atom next to platinum atom, so rather than having a single metal, you are looking into metal alloy in a nanoparticle, nano size. So they have a ruthenium atom can easily convert carbon monoxide into carbon dioxide. The kind of approach that you need to take here is that if I want to form an alloy particle, then I have to reduce the platinum and ruthenium at the same rate. And I cannot do that in a conventional process. It's very difficult to achieve that. So here, what we can do is we can use the sonochemical methodology. So if I go back here, rather than having gold chloride, you will have platinum chloride plus ruthenium chloride. So if you have the mixture of platinum and ruthenium chloride together, the sonicate, you may form an alloy particle. And what we found was initially, rather than forming an alloy particle, we formed a coastal particle. The platinum core, the ruthenium shell. And then we were trying to understand the chemistry behind it. Platinum ions have much lower reduction potential, the activation energy that you need to form the platinum, reduce platinum ions to form platinum atom is much lower compared to ruthenium. So So what happens is platinum ions are getting reduced first, and once you consume all the platinum, then the ruthenium starts to be, ruthenium ions are reduced on top of the platinum, leading to these kind of closure structures. Then we identify this as the Greenwich problem, chemical Greenwich problem. The rate of reduction of platinum is greater than rate of reduction of ruthenium. So then we play with the conditions to make the rates equal, rate of reduction of ruthenium, so platinum and ruthenium equal. That we can do by adjusting the concentrations of the ruthenium and platinum. We take large quantity of ruthenium, less quantity of platinum, so that the rates become equal. By doing that, we were able to generate 2 nanometer alloy particles, platinum and ruthenium alloy particles, that could then solve the problem. So the reason I wanted to kind of show this example is, it is a major research problem, but you can resolve that research problem by simple physical chemistry knowledge. That's the main thing that we have to do. You always need to worry about. If you're doing research, sometimes you may get into trouble, or things may not go very well. But by going back to a simple undergraduate chemistry or PhD chemistry, you may be able to resolve it. And that's where the understanding of the basics is important. So that's basically, I'm not sure what the time is now. So I want to cover various aspects. So maybe I can now move on to the next application, which is polymers. So I want to cover as many areas as possible for you to understand the problem. If I spend more time on metal particles, then I won't have time for processing other things. So now I'm going to give you another example where you can again call this as a green chemistry to form some polymer particles. Now, most of you know what emulsion polymerization means. You check a monomer. Monomer normally will have some sort of double bond, vinyl part CH2CH2 or CH double bond CH2. In this case, I can use the radicals that I generate during the application process to initiate the polymerization. So if you are looking in polymer area or polymer synthesis, especially the radical polymer synthesis, usually what you do, you add an initiator, a chemical initiator. And then the chemical initiator initiates the polymerization process. So in this case, you are contaminating the system by adding an external initiator. Whereas if I use ultrasound, I don't have to add an external initiator because I'm generating radicals by sonication process. So this schematic diagram simply shows what's happening. You saw that video clip that we can make an emulsion, oil and water emulsion very quickly. So normally monomers are hydrophobic in nature. They're like oil. So simply what I do, the physical forces that I generate can be used to disperse the monomer in water. So basically monomer droplets in water. It's like an oil in water, and that's what is happening here. The cavitation process generates shear. That shear generates the monomer droplets. Simultaneously, we also have cavitation bubbles generated. These cavitation bubbles then generates, as I said, some primary radicals, hydrogen and hydroxyl. These radicals can react with the monomer molecule, which are present at the interface, to generate monomer radicals. Those monomer radicals then can diffuse into a monomer droplet to convert the monomer droplet into the polymer particle. It's a very simple way of making polymer particles. So advantages are listed here. No chemical initiators are required because we are generating our own initiators. The reactions normally can be conducted at room temperature. Conventionally, if you do conventional polymerization, you need to do this reaction at a higher temperature. takes more energy. But in sonochemical reactions, you can do the reaction at room temperature, which means if you have some polymers that are temperature sensitive, then sonochemical methodology is better. And now you get very high molecular weight, small particles, and very fast polymerization. Here, for example, we are showing that the polymer particles are around 50 to 60 nanometer in size. So again, this is a real process to make polymer particles. And making polymer particles is with simple properties. It's not that interesting, but you want to functionalize them. So you want to make the polymers more functional. So in this case, what we are trying to do is we are trying to functionalize the polymer particles by magnetizing them. So it takes some magnetic particles or iron oxide particles. We disperse that iron oxide particles into the monomer itself, and then use that monomer to make the emulsion. So when you make the emulsion, each of the emulsion droplet will have this magnetic particles trapped in them. Then when you convert this into the polymer particle, the magnetic particles are trapped inside the polymer particle. That means each of the polymer particle becomes magnetically active. That's what we see here. The polymer particle that we have in this particular case is polybutyl methacrylate, PPGQ, and that is dispersed in certain water as a colloidal solution. So if I put a magnetic piece next to it, because of the magnetic particles being part of the particle, whole solution is magnetically active. So the idea here is rather than having a conventional polymer, if you can make a polymer that is acceptable to your body, then you can use these kind of magnetic particles or magnetic resonance imaging, MRI imaging for biomedical applications. That's kind of proof of concept study that we have here. One thing that I can skip quite a bit is that I can control the size of the monomer droplet that I generate by controlling the power of ultrasound. So if I want to make 20 nanometer particles or 50 nanometer particles or 100 nanometer particles, I can control the size. So again, you can see that I don't add any external forces in the simplest formulation. It gives me to make some polymers that have functionality. I'm just going to extend this to a little bit. Rather than taking a monomer and then converting the monomer into a polymer, you can also take a polymer and then cross-link the polymers to form some structures or again some applications. And for that, we are going to look at what we call the polyphenols. Polyphenols are heavily used in various applications. In food applications, in therapeutic applications, diagnostic applications, cosmetics, and so on. Very common thing that we do is, every time when we have a meal, we are always asked to eat some fruits. So we know why we are taking lots of fruits when we have food. Fruits have what we call polyphenols, and polyphenols are antioxidants. So when you eat food, your system is digesting the food. During that time, when we have metabolic activities happening there, we generate large amount of radicals. During any chemical reactions, we generate intermediates. If these radicals start attacking your cells, then that can damage your cell. Sometimes your stomach cells will die, or other kind of health issues may come. But during that process, if you have some antioxidants like polyphenols present in your stomach, polyphenols like radicals. They attack the radicals very quickly before they attack your cells. That's why we call them antioxidants. and that will follow that. So in this case, what we are going to show is, what we are going to learn is that ultrasound can be used to convert these polyphenolic molecules into nanostructures, polyphenolic nanostructures or microstructures that can be used for delivering nutrients, delivering drugs, and also to avoid any kind of oxidation processes in your body. So if I go to the market, most of us may not have access to fresh foods, fresh vegetables. So what the market is doing, the food industry is doing, is they're extracting the antioxidants or polyphenolic compounds from fruits and vegetables, and then put them into these kind of capsules. That extraction process normally uses some solvent, and during this process you may lose some of the antioxidant properties and so on. So we're not going to go into the details. But the assumption here is that when we take these kind of capsules, we're assuming that we are taking these antioxidants enough for improving our health. But in recent times, the study shows that rather than taking these kind of powdery antioxidants, we have nanoparticles made of the polyphenols. They have much more efficiency in terms of being absorbed in the system that will have health benefit. So if you're looking at the literature, there's a large body of work that is being done where they're taking polyphenolic molecules, example in this case, tannic acid is a polyphenol. You can see large number of phenolic group there. They're trying to convert that tannic acid into polymer molecules, polymer particles, by cross-linking the tannic acids. So large number of large amount of research has been done, being carried out to convert simple polyphenolic molecules into polyphenolic nanoparticles. What we wanted to do was, we wanted whether we can convert the polyphenolic molecules into nanoparticles using ultrasonic or acoustic agitation process. We took a simple molecule which is present in our body, so BTP is one of the enzymes that's being used for various metabolic activities in our body. So we took that compound just as a proof of concept study. We didn't know what we were expecting at that point. We simply solidated that this molecule has this tyrosine molecule. So what you see here is some analytical data. So this is the HPLC chromogram. These are mass spectrometry data. So if I look at the HPLC chromogram, the molecule, parent molecule PPGQ or PPGQ is there. So that intensity of that heat increased as a function of solidation time. Simultaneously, we started making some heat products. One of the products is the hydroxylated product. Other products are higher molecular weight products. The hydrophobicity of some of these products is higher than the parent compound. Then when we took that solution, analyzing that solution by mass spectrometry, we got the molar mass of the parent compound, molar mass of the hydroxylated compound, plus the molar mass of some dimer and fiber molecules. We have taken this molecule. Somehow we are polymerizing this molecule during the solidation process. And that led to the formation of this kind of nanoparticles. So I'm trying to explain the basic part of it, how these nanoparticles are produced by means of the sonochemistry. Okay. So this step we think is happening is that the hydroxyl radicals are generated during the agitation process. You know that. Hydroxyl radical can attack the parent molecule. For example, it can attract a proton, sorry, not a proton, hydrogen atom, leading to this phenoxy radical. Then the radical from the oxygen can migrate to the penetrating itself. And then hydroxyl radical can add to that to form the hydroxylated compound. And also, the phenyl radical can combine with another phenyl radical to form this kind of biphenyl molecule. So that's where basically form a dimer. And that process can repeat itself to form trimer, tetramer, and so on. So what happens is when you change the volume from a monomer to trimer, polymer, once you reach certain limit of the chain length, the solubility of that molecule becomes less. You can reach the saturation level of solubility. Because as the chain length increases, solubility decreases. Once you reach that solubility limit, the molecules, the oligomers, basically collapse into small nanostructures like this. That's what you see in the microscope. Okay. Now you can ask me this question. The whole process is due to the hydroxyl radical being generated and reacting with this molecule. It is simply the hydroxyl radical addition that initiates this reaction. I don't need sonochemistry. I can simply add some hydrogen peroxide. Hydrogen peroxide is a source for hydroxyl radicals. So the question is, why cavitation is important for this process? We cannot simply use hydroxyl radicals to get these nanoparticles. In order to clarify that, we did that reaction. Some of you may have heard about penton reagent. Penton reagent is hydrogen peroxide with a little bit of oil, Fe2+ or Fe3+. So we try to repeat this whole reaction just by adding some penton. We did see the hydroxylated product when we did this in the absence of ultrasonic adding hydrogen peroxide, but we did not see formation of nanoparticles. So the cavitation process in this case not only gives you hydroxyl radicals, it's doing something else so that the nanoparticles are produced. That something else is what is critical here. For example, the formation of this kind of phenyl radical leading to the dimerization of that radical to form biphenyl and beyond that, that's a very high activation. That needs high activation energy. Thermodynamically, that reaction needs more energy. If I use simply the hydrogen peroxide, I don't get that energy. Just by mixing, I can't get that extra energy. So the hypothesis that we have is that these molecules will absorb to the surface of the cavitation bubble. The cavitation bubble is collapsing. During that time, we generate hydroxyl radicals. And also, the cavitation bubbles are heating up. Temperature inside the bubble is going higher and higher. During that time, even though the bubble core may have 2000 Kelvin, that heat can be experienced by the interface. Okay. So the surface of the bubble will have some hot condition, better than or hotter than the solution, but less hotter than the core of the bubble. But that heat that we generate when the bubble is collapsing at the interface is the one that is providing this extra energy, the activation energy for this. So what is critical here to form this nanostructure is not only that we are generating the hydroxyl radicals, but also we need to have that hot interface, cavitation bubble interface. Okay. So that's one example of where we can use this kind of oxidative coupling reaction and the hot condition at the interface or interfacial chemistry to do some synthesize some nanoparticles that have some functionality. Using a similar approach, what we have also done is we developed a methodology to form core-shell microspheres and also nanospheres. The purpose of these core-shell particles, mainly microspheres, is to encapsulate either a drug or a nutrient for various applications. Here, I'm just showing the product that is generated, but I'll go through the mechanism later on. So if we are taking some biopolymers, example, milk protein, BSA, chitosan, take any biomolecule or biopolymer, and then dissolve that in water. Let's say, for example, if I want to encapsulate fish oil or vitamin. Fish oil and vitamin, most of these kind of nutrient compounds are hydrophobic in nature, they are oily in nature. So we already know that anything that's oily, I can make an emulsion. In this case, I make an emulsion of that nutritional compound or a drug. Then that emulsion will be covered by the protein or the biopolymer. The biopolymers are surface active. And then what we can do is, by using the small amount of oxidative radicals that we generate during the application process, we can cross-link this molecule upon the thin shell. It's not like a molecule simply absorbing, we are also cross-linking them on a thin shell. So once you form this thin shell, then whatever you have encapsulated inside is completely protected. Let's kind of go back one step and think. I want to add some fish oil or some nutrients into a food matrix, let's say yogurt or a fruit drink. The option for me is to take the fish oil, put it into the fruit drink or milk and food yogurt and just mix it. Okay. Of course, you can do that. After you mix it, you store it in some place. All the food material, yogurt or fruit juice, everything will have oxygen. So what will happen? These kind of compounds, fish oil, vitamin, everything, they are prone to oxidation. Now you have a direct contact between oxygen and that molecule, it gets oxidates, and then it loses its functionality. But instead, that's the conventional methodology. But instead of simply mixing it, by encapsulating this shell, and then if I put this functional material into the food matrix, then I can kind of store it for many weeks or many months. It is completely protected from the oxygen because of this shell. So that's the purpose of this book. The purpose here is that we encapsulate functional materials, store them, until you consume them, they are protected. And the chemistry behind it is again a little bit of complex. In this case, we are just forming air-filled microspheres. Things of air can have oil also. You take the protein, dissolve it in water, and then the protein gets absorbed, and then simply cross-link them. Maybe I don't have the reactions here. The cross-linking is due to the hydroxylate receptor. They cross-link, but exactly what we do is going to cross-linking that we are doing. Here the cross-linking is between molecules, simple molecules. Here the cross-linking will be between biopolymers. Same methodology. Here I'm showing that I can encapsulate doxorubicin, it's a cancer-active drug. And then you can use this for targeted drug delivery. For example, I can functionalize the shell, inject into my body, and then the microsphere goes to only tumor cells where you can release the drug and so on. And here I'm just showing, we may not have much time. For when these protein microspheres, I should be able to control the size and size distribution. I can play with my also conditions to make bigger microspheres or smaller microspheres. We won't have time to go through this in detail, so I'm just going to skip it. So I'll just show you a couple of more applications whether we will solve. Here, the project was done for Cadbury chocolates, where they wanted to encapsulate flavor. And then the flavor encapsulator microspheres can be put into cocoa butter that can be used for making chocolates. The advantage here is that, again, conventionally, if you want to make these flavored chocolates, you mix this flavor with some silica particles and spray it right down. During this process, you are heat treating the flavor, so you lose the functionality of the flavor. Whereas if you use the ultrasonic emulsification process, it is pure flavor protected from the environment that you can encapsulate, and the quality of the flavor chocolate is 100 times better than the normal flavor chocolate. A similar approach we have taken for Gates Foundation. Gates Foundation wanted to use the similar technology, but rather than encapsulating flavor, they wanted us to encapsulate vitamins and nutrients. The idea here is that, if you go to some parts of the remote parts of some countries, including India, there are children, they don't get proper nutrients. They don't have access to nutrients. You can send nutrients to them in bottles, but they won't survive in terms of the transport or storage for a long time. Some places they won't even have refrigeration. Okay. So what you need is, you need to send this nutrient which can be stored at any condition without losing its functionality. So the approach is simple. We use the same methodology that we are doing is here, putting the vitamins in these microspheres, and then using the, some protein shell, and then we can kind of incorporate that into the flour. For example, if we want to make biscuits or some rotis, biscuits and rotis, you can store them for biscuits, especially you can store them for a year or two. So once we encapsulate and then put them and store them for long enough, and then until you eat the biscuit, the nutrient will have its own functionality. You're not going to lose the functionality. And we demonstrated that we can put them into, in this case, for example, making some rotis or chapatis, so you fry it in pan. And after you fry it, you will dissolve that roti into a solvent and then look at the nutrients. And they still have the same nutrients without any changes. And then we propose to them that this could be scaled up to large quantities or larger amounts for manufacturing and sold to, not sold, but even to send it to various parts of the world. The Gates Foundation is considering that. A similar approach can be taken for making some emulsion gels, pharmaceuticals, and so on. I think I'm running over time, so I'm just going to. Here we have recently developed a shear-based technology to make some emulsion gels without adding thickeners or emulsifiers. So again, technology. This technology is currently being discussed with some commercial partners for commercializing these things. But I think we'll take another 10 minutes for me to properly explain to you. So better that I just skip here. We're also using ultrasound technology to form some biofuels from algae. Not only that, we can extract more oil from algae, but also we can separate the emulsion to get a better quality oil. In this case, if you want to extract an oil from a plant, what you do, you just crush it. So you take a fruit or vegetable, you crush and get the oil. But you're not only getting oil, you're also getting proteins and biopolymers coming out. So you're getting an emulsion. From the emulsion, you have to separate the oil. And that process is very, very expensive. And we have developed a shear-based technology simply by sonicating in 5 seconds. You can separate the emulsion. So here, we have this green algae paste, which has the omega-3 the biofuel. If you are able to just click on you see that just 2 seconds or 3 seconds of sonication, you can get the emulsion separated. It's very, very useful for oil industries. That's something that I have talked to the person close. Here you have lots of oil industry. The emulsion separation is very simple, clean, no solvents added. Then we are also working with some collaborators on food basis processing to get some useful compounds. I know I kind of touched at the end a little bit, but you can see ultrasound interacting with bowls in a liquid can be used in many fields. I have shown some food applications, biomedical applications, materials applications, and so on. So hopefully you got some overall picture of what can be done using ultrasound. This may be useful to your project, may not be useful, but some of the basic things that we learned may be applicable to either current project or future projects. With that, I would like to kind of let you read the summary. Thank you again for listening to me. I think I went moving forward in terms of time. Hope we have enough time for some time for asking questions. I'm happy to answer questions. And again, thank you for listening.
Lucas?
Aqui. So I have a question about the synthesis of nanomaterial. You said that the nucleation rate would be higher to make smaller nanoparticles. But in the synthesis, does it have to use ultrasound for all the reaction, or we can use like ultrasound burst or pulse in the beginning, in the nucleation, and the rest of the synthesis in a silent condition?
Okay, I think there are two ways there, because if you are only using ultrasound with no chemicals added for the reaction, then you have to have the ultrasound on all the time until you finish the reaction. But if you are doing a reaction which is driven by chemicals, so you already have a reducing agent, and you want to change the properties of mass transfer, then you can use pulsing. So it depends which approach you are taking. Here also you have to have the tools of sonation. But even for having that mass transfer effect, even if you don't want to do continuous, at least every minute a short pulse, so to kind of change the properties of the material. That's
Thank you for the presentation. My question is about I would like to know if you have a specific preference for the light function or a range of
so the question is, if you want to make an emulsion or for a particular application, is there a single frequency you can use or many frequencies? So I think again, because we only have a short period of already go through the frequencies, like in general, low frequency, 20 kilohertz, you will have strong shear force, single force, less radicals. That is good for food applications, biomedical applications, and also some of the encapsulation studies. Reason for that is when you have less radicals, then you do less damage to the functional compounds. When you want to encapsulate like vitamin or fish oil, during that process, I should not affect the functionality of this, I should not change the compound to something else. And because those kind of shear or the emulsification processes only take 10 seconds, 15 seconds sonication, you don't normally affect them. So for those kind of applications, low frequency is good. But if you want to do material, like nanomaterial synthesis, then you want large quantities of radicals, then you go to high frequencies, like 200 kilohertz, 300 kilohertz, those kind of things. Commercially, most of the units operate around 20 kilohertz, maximum 100 kilohertz. Because most of the applications are for processing, not for synthesis.
Mais alguém? Christian?
Good morning, Professor. Thank you for the presentation. I have a question about the calculated nutrients. How is the stability of the calculated nutrients?
The question here is how the encapsulation increases the stability. Let's say most of the nutrients are prone to oxidation or prone to sunlight. So if I mix or
if I store it in normal place where it is exposed to oxygen, even within a few days, the compound, like fish oil or vitamin E, will be oxidized. That means it loses its functionality. But when you put a thin film of protein or biopolymer, then this acts as a barrier between oxygen and the compound that we are encapsulated. So until you break the shell, thin shell, it is protected from the oxygen. So that means I can store it for 1 year, 2 years. As far as I don't break the shell, then it is safe. So that's the way its stability comes. There's a physical barrier between your compound and oxygen environment that we are creating. And that seems to be very efficient.
Mais alguma pergunta?
Regarding the encapsulation processes, the first part of the question is a bit similar to what I was asking. Usually there is one type of intensity of ultrasound that is used, or is there a range of intensities that can be applied for those applications? And the second part of the question is about the ultrasound systems used in this process. Pros or bad?
That's why I skipped a little bit here. So here, for example, to change the properties of these microspheres by changing the acoustic energy. So you can control the power. So they want to make this material shell thicker or thinner, I can change the ultrasonic power. Okay. And it is critical for some application. I think I told you that if I want to inject this into my body for ultrasound contrast or blood delivery, the size distribution has to be 1 micron to 5 microns. Above 5 microns is there, it's going to block you to bleeding and so on. So all these things can be controlled simply by changing the power density of the ultrasound. Majority of the cases, this is done by GCV probe. Ultrasonic bath, you cannot use it. Ultrasonic baths are very low power density because we use large volume of water. And you cannot use very high frequencies because no emulsification you have. So pretty much you are playing with a simple parameter, which is the power density. Frequency is almost
Pessoal, thanks, Professor, for your lecture. We know that there is a bit difficult for we process taken by ultrasound from a laboratory scale to an industrial scale. Your opinion, what's missing was reach this step?
I think it's a really good question. We are going to discuss that as part of the discussion for the course. Very often, these kind of things are driven by demand. So let's assume that I have developed this technique, and I have shown that this is working at the level of the scale. And then I go to the manufacturer, and I say that, hey, this can save this much money and so on. But someone has to do the next level critical unit, like pilot scale unit or next unit. Yeah. So at that point, if it is just me that I need that unit, then the cost of that unit is going to be much higher. But if there are hundreds of us needing that unit, then the cost per unit will decrease. So very often that's very difficult to convince the manufacturer that that we're getting demand in 5 years' time. Can you reduce the price? They will say, no, for us to construct one unit, it is going to cost us say $500,000 or $200,000. And very often as researchers, it's very hard for us to find money. Then you approach another industry to support it. So it is always a compromise between researchers, industry, industry people and manufacturers. What I know is currently there's a large number of reactors, PP reactors, that is used for water treatment, sludge treatment, water treatment. In Europe, there are big scale units available. But food processing, at this stage, there's no big demand. Some of these kind of things. That's why we propose this to Gates Foundation, that we can build a unit that can make, say, 100 kilograms a day. But even though we can kind of come up with set of schematics, they still have to go to a company who can make it. And that's where we are in that transition. People have not fully realized the importance of this kind of work. So we're just waiting, we're currently negotiating a number of companies and so on. So except for wastewater treatment and also maybe dairy processing, and also in pharmaceutical industry, they use it for sonochemistry purposes. There are active areas where peak ultrasound units are being used. In food and biomedical applications, it is still underdeveloped. But I will be sharing some more details this afternoon when we go to the large-scale reactors as part of the course.
The last question is.
My question is about the encapsulation also. But you told us that you have a recirculation of the solution. Encapsulation. How can you establish that the ultrasound will not degrade the capsule that you are forming, and which technique do you use to evaluate this?
That's a really good question. Not just for that. Anything that you do is ultrasound. How do you know that you're not damaging the functionality of the original compound? In this case, what we're showing is we're showing that we're using HPLC. Look at the vitamin E. This thing that we can see is the retention time of the vitamin E before and after sonication is not changing. That means we are not affecting the compound. We don't see any new peaks produced. That means we are not producing new products. But that's only for the physical quality. I have also checked the functionality. Functionality is, for example, antioxidant activity or any other functionality. So there are kits available, analytical kits available. So what we do is we check the fish oil and then look at the antioxidant activity of the fish oil before sonication. After sonication, we break these capsules, collect all the fish oil in the sanction. The same thing is happening here also. Here, that's what we are showing. We are showing all the functionality of the materials that we have encapsulated. We show that none of them changes. And you can understand that why. Because the process only takes few seconds. Within a few seconds of sonication, then you form these microscales. So within a few seconds, you're not going to generate large amount of values that are not going to damage it.
Devido a adiantado da hora, tem que começar o curso mais tarde, o vai até a sexta-feira. Mas ele vai ficar pela tarde, amanhã, se tiver alguma dúvida, quiser contato, pode falar comigo, com o professor César.
E a gente pode realizar uma